In this section, we were going over homogeneous linear equations with constant coefficients, which was a very intimidating name for one of the easier methods I think we cover in class. So I told you that we would talk about the type of ODE we're solving, describe the general approach, and then look at a couple quirks that emerge from repeated roots and complex roots, and then talk about what this means for spring behaviors, which is related to your project. So the specific form we have is right here, which it still looks a little intimidating in that form, but really it's just when you have numbers multiplied by derivatives of y and everything's linear and there's nothing on the right-hand side. And our approach is always just going to be to assume y equal to e to the mx is a solution, plug it in so that we have an algebraic equation to solve for m, and then just our solution tends to be a linear combination of exponents, unless we're looking at repeated roots or complex roots, which need special rules that we went over later. So we did our first example. It was just kind of a normal one without any repeated or complex roots. So we had those nice exponential solutions. And then we did an example where we don't get enough roots and we have to deal with repeated roots. And I sort of gave you the solution as we were working through the example, but then we talked about the rule. And what's kind of neat is you could actually find this rule for the first root. If you were solving this problem right here, you could use the method that we learned before this, reduction of order, to actually find that repeated root solution, which is fun. So the next thing we did was we started talking about spring models, and that led us to our first imaginary roots. And we talked about how there's a special formula that converts imaginary exponentials into cosines and sines. And so I wrote down the forms of the functions that you can use instead of those imaginary exponentials. And we finished our example out by changing into cosines and sines and solving for our initial conditions as coefficients, C1 and C2. And then we looked at a damp spring in general for sort of unknown parameters that we named 2 lambda and omega squared. And we talked about how depending on which is bigger, you might have a couple different types of behavior. And then we actually looked at those examples of kind of a spring the way you'd expect it, a really damp spring that kind of settles down very quickly, and then a breaking point where a repeated root lets us have a sort of complicated behavior leading into that second case. And then we just wrote our rules for repeated roots and complex roots in one place and put the two together for repeated complex roots in the way you'd expect. So right here I just wrote like the 3 main points from that. If you have constant coefficients, assume y equals e to the mx and then plug it in and see what happens. If you have repeated roots, then we have to add powers of x until we have enough solutions. If we have complex roots, we use that formula, it's Euler's formula, and it just turns it into sines and cosines for us. And then kind of like a sub-point is that this approach hopefully is starting to feel kind of familiar, where we assume y is something and then we plug it in and see what happens. It's a really common tool for dealing with ODEs. And so if you're ever sort of unsure about what to do when we're solving ODEs, just remember that if you think y could be something and you plug it in and you find out how to make that work, that's a valid way to solve your problem. Your practice problem for this week, or this class, sorry, is just going to be to solve y double prime plus 4y prime plus 7y equal to 0. And hopefully that won't take you too long. So just work on that, and then I will see you in class.